Hi, my name is Adam Katona. I'm a PhD student at the University of York. In this talk, I will present my work on how we can learn to predict and optimize for evolvability when using indirect encoding. And I will discuss how this approach can be used for artificial gene regulatory networks. This talk will have four parts. First, I will talk about what is the problem we're trying to solve, the meta-learning problem. Then I will talk about why indirect encoding are important and how nature can find good indirect representations via the process of evolution of evolvability. Then I will propose an approach to learn good indirect representations with our machine learning systems. Let's start with the meta-learning problem. Meta-learning is about learning to learning something about the learning process using our past experience of learning in training environments. The aim is that when we are presented with new unseen environments, we can learn faster. An example of a meta-learning problem is MetaWord. Here we want to use reinforcement learning to learn to perform tasks with a robotic arm, like manipulating different objects. The idea is that we can learn something about how to solve these kind of tasks, so when we are presented with a novel situation, we can use this knowledge to learn faster. Another area where meta-learning can be useful is few-shot classification. Here we have to learn a classifier, but we are only given a few examples of each class, even only one example. To use meta-learning, we can learn something about how to solve few-shot image classification for these kind of images by collecting a lot of experience solving many of these problems. Then we hope that the knowledge we learned will generalize to different kind of images as well. So meta-learning is about learning something about the learning process. But what can we learn? A somewhat less exciting approach is to learn hyperparameters or network architectures. But we can learn more complex things as well. We can learn optimizers, which change their behavior depending on the context. In case of reinforcement learning, we can learn intrinsic reward functions. Or we can learn good initial parameters, which allow us to learn fast in many situations. This last approach works surprisingly well. For example, the model agnostic meta-learning does this, and it is the state of the art in many of the benchmark problems. The aim of our approach, on the other hand, is to learn good indirect representations. Now let's talk about why we should use indirect encoding. Direct encoding is when every aspect of the system is encoded as a separate parameter. For example, there is a separate parameter for each weight of a neural network. Direct encoding works very well with gradient descent, and it was even demonstrated to work well with evolutionary algorithms. So why should we use indirect encoding? Biological evolution uses indirect encoding, but it is something that is an important aspect of evolution success, or evolution could be just as successful with direct encoding. I will argue that it is an important aspect and we should aim to use indirect encoding as well. By using an alternative representation, we can transform a complex fitness landscape to a simple one. In this simple example, we have a function which is massively multimodal. By using the alternative representation of the wave number and the phase, we can transform this to a very simple function with a single peak, and the problem becomes very easy to optimize. The previous example was quite simple. What are some techniques that can be used to indirectly encode solutions to more complex problems? I will mention two of these. One example is the artificial gene regulatory network. The idea is that we have a bunch of genes which can be expressed to create proteins. However, each gene can be regulated by other proteins, and we get a regulatory network which can have complex dynamics. We can represent the dynamics of dynamically changing protein concentration levels by encoding the weight of this regulatory network. I will talk more about gene regulatory network in the second half of the talk. Another indirect encoding technique is hyperneat, which is a technique to indirectly represent neural networks. The idea behind hyperneed is to assign coordinates to each node of a network and use these coordinates to query the values of each weight from another network. This other network is called the pattern-producing network, and it is well suited to generate repeating patterns with variation. We looked at a few examples of indirect encodings, but why should we use such techniques? One property of indirect encodings is that they can reuse parameters multiple times, which allows the creation of modular and regular designs. Nature's encoding is incredibly modular. In the fruit fly, for example, a few mutations can add new pairs of wings or make them grow legs instead of antennae. Or artificial indirect encoding techniques are not this impressive yet, but there are a few success stories. One is the result by Google DeepMind, where a pattern-producing network was used to generate the weights of a fully connected network, and it learned to generate a convolution-like structure and outperformed direct encoding on an image reconstruction task. It could discover that convolution works really well for vision automatically. We already knew how well convolution works, but who knows what kind of other structures exist that work also really well, but we have not yet discovered them. Using indirect encoding can allow us to potentially learn these effective structures automatically. Another property of indirect encoding is the ability to change the sensitivity of certain traits via developmental canalization. This property allows us to direct the search toward promising areas of the search space. We already have algorithms which are programmed to do this. For example, CMA-ES is one of the most successful black box optimization algorithms. It learns a Gaussian distribution of how to vary the parameters. With indirect encoding, evolution have the power to discover advantageous distributions automatically. There is no need to program it in. I will talk more about why indirect encoding have this property in a few slides. But how can we find good representations? Using the right representation can make problems look easy, but because indirect encodings are so powerful, it is just as easy to make the problem even harder. How did nature come up with these successful indirect representations? Now I will talk about how evolvability is a good measure of the quality of indirect encoding and how evolution is able to evolve evolvability. Evolvability is a measure of potential for future improvement. Here, we are concerned with the ability to generate good quality variation. Definitions disagree on what counts as good quality. Some define it as variation which is adaptive, other that variation which is innovative or novel. But how can evolution modify its own evolvability? It is possible because of the developmental system. Mutations are random. Evolution does not have control over them, but the developmental system turns these random genotypic mutations into a biased distribution of phenotypic variation. The way this is possible is somewhat similar to how a generative adversarial network can learn to generate any distribution from random noise. We can train the developmental system to turn random mutations into a distribution of phenotypic variation, which has more evolvability. But even if we have the capacity to learn, how do we know what to learn? What distribution will be more evolvable? The answer is that we can generalize from past experience. If some aspect of the developmental program was useful in many past environments, it might be useful for future environments as well. For example, it might be a good idea to vary the length of the legs of an animal, but we probably don't want to vary the length of the left and the right leg separately. We can remove this risky independence by changing the developmental process to always make the legs equal length. This is an example of a deep structural regularity, which was useful in the past and will probably be useful for the future as well. But even if we have the capacity to learn and we have the experience to learn from, what drives this learning? This is a difficult question. natural selection cannot select for evolvability because it is a measure of future yet unrealized potential. Even though this is a really interesting question, for the purposes of this talk, we don't need to have an answer. Our aim is to make better machine learning algorithms, and we have a lot of freedom when designing our algorithms. We can select directly for future potential if we can calculate it. We can remember and learn from a practically unlimited amount of past experience. And this experience can come from many sources, compared to biological evolution, where we can only use the experience of our ancestors. Next, I will talk about our proposed approach to learn evolvability. As an overview so far, we want to solve the meta-learning problem by collecting learning experience and learning good indirect representations. This is possible because a well-chosen representation can generate good quality variation. We use evolvability to evaluate the quality of our representation. The core idea of our approach is to learn the patterns which cause evolvability in many training environments via supervised learning. Once we know these patterns, we can optimize for them in new unseen environments, which should allow us to learn faster. In order to learn the patterns which cause evolvability, we designed an iterative algorithm. Step 1 is to collect a dataset of developmental program and evolvability score pairs. Once we have a large amount of data, we can use supervised learning to train the evolvability model to predict the evolvability of a developmental program. Step 2 is to use the evolvability model to jointly optimize for fitness and evolvability. This allows us to collect data to specifically test if these patterns really cause evolvability or we have overfitted the evolvability model. Then we can go back to step 1 and use our new data to train a new evolvability model. The algorithm works like the scientific method. We collect data, we create a hypothesis, and we collect more data specifically to test this hypothesis. To better understand what this approach is trying to do, I will introduce the analogy of software development. In this analogy, direct representation of a program is the generated machine code, which the CPU actually executes. Indirect representation of a program is the code in higher level programming language. We want programs which are reusable, easy to add new features, and hard to introduce bugs. This is similar like how we want our indirect representation to be modular and have selective sensitivity. Programmers look at past experience and come up with guidelines. These are very similar to the deep patterns what the evolvability model wants to learn. The programmer are trying to write programs which solve a task but also adhere to the guideline. This is like when we jointly optimize for both evolvability and fitness. We are, in a sense, learning guidelines of how should an indirect representation look like if it wants to be evolvable. Now I will talk about some early experiments we did to apply this approach to gene regulatory networks. We used a common meta-learning benchmark problem, few-shot image classification on the omniglot dataset. The dataset contains a few examples from 1500 different characters. This is basically the transpose of MNIST. Our model was a convolutional neural network, but we generated the weights of this network with a gene regulatory network. To determine the weight, we sampled the protein concentration at specific times. The system is able to achieve around 60 to 80% validation accuracy. It is worse than the direct encoding, but this is expected since indirect encodings are generally harder to optimize. To train the evolvability model, we first collected an evolvability dataset. This contained the generated trajectories to represent the developmental programs and the final validation accuracy to represent the evolvability. We used a 1D convolutional network for the evolvability model. We used gradient descent to train everything. In this diagram, we can see 250 independent training runs sorted by their validation accuracy. The blue curve is the actual validation accuracy, and the orange curve is what the evolvability model predicted. The curve is much more noisy in reality. It was smoothed to see the trend. The evolvability model was able to differentiate between good and bad representation to some degree. However, when we use the evolvability model to jointly optimize for evolvability and fitness, the performance did not improve. This can be for several reasons. Maybe the evolvability model overfitted to the data. Or more likely, even if we can predict evolvability, it is hard to find good representation since there are many local optima. It was interesting to see what kind of behavior did the evolvability model liked or hated. On the left are some trajectories which were liked by the evolvability model. On the right are some trajectories which were hated by the evolvability model. This is still a new approach, and there are many open questions. Do you think this approach can work on practical problems? I'm looking forward for discussions on the workshop website. Thank you for listening.